Hello everyone, in this presentation, our group will be focusing on the basic principles of separating ions based on mass to charge ratio in mass spectrometry. Mass spectrometer generates multiple ions from the sample under investigation. It then separates them according to their specific mass to charge ratio, and then records the relative abundance of each ion type. Mass analyzer plays a very important role in separation of ions. It is a component of the mass spectrometer that takes in ionized masses and separates them according to their mass to charge ratio. We will be looking at 5 different types of mass analyzers: time-of-flight mass analyzer, magnetic electrostatic double sector mass analyzer, quadrupole mass analyzer, quadrupole ion trap mass analyzer, and ion cyclotron resonance. First of all, let's look at time-of-flight mass analyzer in greater details. Time-of-flight TOF mass analyzers measure the time taken for ions of different masses to move from ion source to the detector in the absence of magnetic or electric fields. Kinetic energy and velocity of ions affect the separation of ions. Given the length of drift tube L and the voltage from the ion source V, the time of flight of ions can be calculated by taking L multiplied with square root of m over z and 1 over 2v. When L and v are constant, it can be seen that the time of flight of ions is directly proportional to square root of m over z, showing that the time of flight is dependent on the mass to charge ratio of ions. This diagram shows the time of flight mass spectrometer with a reflectron. Take note that the drift tube is a field-free region in which the ions travel from ion source to the detector. Reflectron is present in some of the time-of-flight mass analyzer. Reflectron is added to the TOF mass analyzer to improve the resolution of the mass spectrometer, especially of the higher masses of ions. The function of the reflectron is to reflect the ions that passes through the reflectron in the opposite direction. Compared to ions with lower kinetic energy, the ions with higher kinetic energy penetrate deeper into the reflectron and will take a longer time to reach the detector. The purpose of the reflectron is to adjust the flight time of ions such that the ions with same mass to charge ratio and different kinetic energy reaches the detector approximately at the same time. Time-of-flight mass analyzer has some advantages. TOF is the fastest mass analyzer with high ion transmission. Also, a larger range of mass can be used among all other mass analyzers. However, TOF has a poor resolution as compared to the other mass analyzers.
The second type of mass analyzer is the magnetic sector mass analyzer. Let us now explore the basic concept behind the magnetic sector mass analyzer. In this analyzer, ions leaving the ion source are accelerated to a high velocity. The ions then pass through a magnetic sector in which the magnetic field is applied in a direction perpendicular to the direction of ion motion. When force is applied perpendicular to the direction of motion of a particle, there is no work done on the particle and its velocity remains constant, but the particle travels in a circular path. Basically, the ions of a certain mass to charge ratio value will have a unique path radius which can be determined if both magnetic field B and voltage difference V for a region of acceleration are kept constant. When similar ions pass through the magnetic field, they will be deflected to the same degree and follow the same trajectory path. Ions are brought into focus at the detector slit at different magnetic field strengths. To achieve better resolution, an electric sector that focuses ions according to their kinetic energy can be added to the analyzer. Like the magnetic sector, the electric sector applies an electric force perpendicular to the direction of motion. We will now look at a double focusing magnetic sector mass analyzer, which utilizes both magnetic force as well as electric force to separate the ions. In stage 1, the sample is vaporized and then ionized by being bombarded by a beam of high-energy electrons. The electron beam knocks out an electron from the molecule of the injected sample, creating a molecular ion. Next, there is a pair of oppositely charged plates in the ionization chamber. The positively charged plate causes the positively charged radical cation to accelerate into an analyzer tube. A voltage is applied across these plates to bend the ion beam as it travels through the analyzer. The analyzer tube is surrounded by a curved magnetic field which causes the path of the radical cation to be deflected in proportion to its mass to charge ratio. The flight path of the ion depends on its molecular mass, its charge, and strength of the magnetic field. Ions in the sample separate into different specific trajectories upon applying magnetic field. The selection of ions is achieved by the fact that only ions traveling on a path with a narrowly defined radius will go through the exit slit to the detector. Hence, the more narrow the slit is, the higher the resolution of the device, and a more accurate spectrum of ions is obtained. Next, we will look into why a specific value of mass to charge ratio results in a specific trajectory of the ion by analyzing some of the equations involved. As moving charges enter a magnetic field, the charge is deflected to a circular motion of a unique radius in a direction perpendicular to the applied magnetic field. Ions in the magnetic field experience two equal forces, force due to the magnetic field as well as centripetal force. By equating these two forces together, we get the following equation, which is QVB equals to mv square over r, where Q is the charge of the ion, V is its velocity, B magnetic field, m is the mass of the ion, as well as r is the radius of the path taken. Solving this, we get r equals to mv over qb. This shows us, and further manipulation gives us, that r equals to square root of 2v0 over qb square, where v0 is the voltage applied. And this shows that r is only dependent on electric potential and magnetic field, hence an increase in the magnetic field while keeping the v0 constant causes the r to decrease. Since the gain in kinetic energy of the ion is equal to the work done by the electrical potential energy, we can equate these two energies together to get half mv square equals to q times v. And by manipulating the r equals to mv over qb, we can get v equals to bqr over m. And we can substitute this v into the kinetic energy equation. And so we can get m over q equals to b square times r square over 2v. From this equation, we can see that changing the magnetic field will change the r of the path accordingly, allowing us to determine the various m over q of ions using this method.
The third type of mass analyzer is quadruple mass analyzer. As the name implies, it consists of 4 cylindrical rods which are set parallel to each other. As shown in the figure on the right, the combination of radio frequency and direct current voltage creates a region of strong focusing and selectivity known as a hyperbolic field. In simpler terms, a radio frequency voltage is applied between the two pairs of rods so that ions will then travel from one terminal to the other. Only ions of certain mass to charge ratio will be captured by the detector. On the contrary, all other ions that do not have a stable trajectory will then collide with the quadruple rod. By varying the radio frequency voltage applied to the system, we are able to select ions with a particular mass to charge ratio. After these ions are selected by the detector, the signal is boosted by an amplifier, which is subsequently sent to a computer that converts the electric impulses to visual displays and hard copy displays. It's important for us to take note that RF voltage and DC voltage must be applied simultaneously to the system for mass spectrometry. In a case where only RF voltage is applied to the system, the ions will then crush into an electrode when the ion charge is large or the ion mass is low. Positive ions will move between negative rods horizontally, whereas negative ions will move between positive rods vertically. Quadruple mass analyzer is commonly used in classical mass spectra due to the ease of operation and good reproducibility. The switching between the positive and negative ions can be simply achieved by changing the direction of current flowing in the RF circuit. In addition, quadrupole mass analyzer is also known for its good tolerance of high pressure. Compared to other methods of mass spectrometry, quadrupole mass analyzer has a relatively low cost. When we consider the limitation of quadrupole mass analyzer, the first thing that comes to mind is its limited resolution. Notice that increasing the resolution will decrease the number of ions that reach the detector. Thus, in order to obtain a reasonably large sample size, the resolution of the equipment has to be compromised. Moreover, quadrupole mass analyzer has a limited mass range up to 3000. Thus, it's not widely used for more advanced research.
The fourth mass analyzer that we will be talking about is the quadrupole ion trap mass analyzer. This mass analyzer is made up of a ring electrode and 4 grounded end cap electrodes. It also uses an electric field to trap ions and separate them by their mass to charge ratios. An alternating current is applied to the end cap electrodes, while a direct current is applied to the ring electrode. So, before I begin explaining on how the quadrupole ion trap mass analyzer works, let me briefly introduce ion trapping. What is ion trapping? An ion trap is a combination of electric or magnetic fields used to capture charged particles such as ions in a vacuum. The ions will be trapped at the most stable point that you will see later on in the slides. So, how does the ion trap work? The application of voltage to both the ring and the end caps leads to the formation of a potential well. The most stable point in this diagram is in the center of the well, where the potential will never move up or down as the field rotates. The larger ions tend to end up in the middle of the well due to its large inertial. Similarly, the smaller ions will orbit around in circles. As the radio frequency voltage increases, the heavier mass ion orbits become more stabilized, and the lighter mass ion orbits become less stabilized. This causes the lighter mass ions to collide with the walls, thus eliminating the possibility of it getting to the detector. For example, take the blue ion here as an unwanted ion. This will be its trajectory. It will leave the ion trap and not reach the detector. On the other hand, the selected trap ions will be ejected as the red ion here. This is its trajectory. The ejection is done in order of increasing mass to detector by gradually increasing the applied RF voltage. The ejection of ions to the detector creates a series of ion signals dispersed in time. This constitutes a mass spectrum. Using the Matthew map parameters, the motion of the ion within the trap can be governed, and a stability diagram can be derived. The equations are placed in the slides where Q and A are the Matthew parameters. The ions that can be stored in the ion trap have stable trajectories in both the radial and axial directions simultaneously. Such trajectory stability is obtained in the region closest to the origin, and in this diagram, it is region A. While region B is also stable, its importance in the quadrupole ion trapping is still being studied at the moment. Resonance excitation plays also an important role in this mass analyzer. Resonance excitation is the supplementing of potential oscillating at the axial circular frequency of a specific ion species. This excitation causes specific species to move away from the ion trap, causing the species to experience a greater trapping field. Additionally, the resonance excitation is used for at least 3 purposes in this mass analyzer: to remove unwanted ions and increase the kinetic energy of ions for ejection and detection. To conclude, the ion trap analyzer will select for ions whose mass to charge ratio is targeted. Additionally, this device has a high scan speed and high sensitivity, which has led to a significant increase in usage amongst researchers today.
The fifth mass analyzer is ion cyclotron resonance. ICR is an ion trap that uses a magnetic field in order to trap ions into an orbit inside of it. In this analyzer, there is no separation that occurs. Rather, all the ions of a particular range are trapped inside, and an applied external electric field helps to generate a signal. When a moving charge enters a magnetic field, it experiences a centripetal force, making the ion orbit. The frequency of the orbit depends on the charge and the mass of the ions. not the velocity. If the magnetic field is held constant, the mass-to-charge ratio of each ion can be determined by measuring the angular velocity. The relationship is that at high angular velocity, there is low mass-to-charge ratio, and at low angular velocity, there is high mass-to-charge ratio. Charges of opposite signs have the same angular velocity. The only difference is that they orbit in the opposite direction. If the energy is provided at a frequency equal to their precession frequency and in a direction perpendicular to their plane of precession, ions will absorb the energy, enabling them to be detected. Here are some advantages of ion cyclotron resonance. First of all, it has the highest recorded mass resolution of all mass spectrometers. It also has powerful capabilities for ion chemistry and tandem mass spectrometry experiments. It enables non-destructive ion detection and ion remeasurement. It also enables stable mass calibration. Of course, ICR has some limitations. It has limited dynamic range. Its strict low pressure requirements mandate an external source for most analytical applications. It is also subject to space charge effects and ion molecule reactions. Here comes to the end of our presentation. Thank you very much. I hope you all enjoy our video. Keep calm and love chemistry.